So, hello everyone, welcome to the next lecture. So, today we are going to look at some thermodynamic potentials which are going to come back and back at you in this course on material growth, especially the Gibbs free energy that I am going to discuss today. But so like we ended the previous class by saying that so it is important to define rules that tell me how the system is evolving, how the system is evolving, not how the universe is evolving, okay? And that is what defines the motivation for defining some of these potentials which are of interest to us, okay? So we will see how to define them, how to interpret them, and so on and so forth. Okay, so before that, so let us again go back to the definition of entropy. Entropy, we said, is going to be calculated. The recipe for calculation of entropy is delta Q reversible by T, and that is nothing but so from the first law, now I can invoke some first law of thermodynamics and say that this is du plus PdV, or so the work done, which is the PdV term, divided by T, right. So, delta W, I think I did not do this, but delta W is PdV, right, just for mechanical work, right. So, if I have other works that are there, then I am going to say that that is equal to PdV is the mechanical work minus E times dq is the electrical self energy or work done, right. So, if I apply some charge, there is some electric field that is generated, and E times dq. So, both of these have some some cause and effect relationships, right. So, these are conjugate variables, or dH times magnetization, right. So, minus of that, right. So, this is the work done on the system, okay. Okay, so this is the PdV work on the system, and so this just comes from first law of thermodynamics says that du is equal to what is it, delta Q minus delta W. So, I just wrote U plus delta W equal to delta Q, right. So, and for a reversible process, this is just du plus PdV equal to delta Q, and then if I divide everything by T, that is my ds, right, in a reversible process. But so eventually it becomes a state variable. So, whatever I am going to define, I am just going to remove these delta Q's, right. So, from this equation, the path variables, right. So, delta Q's and delta W's are going to be removed from equations, and I am just going to make everything in terms of, write everything in terms of state variables, okay. Now, with this I can then say that du equal to actually TdS minus PdV, right. So, this is the delta W, this is the delta Q, but in a reversible process, but so when I am talking about things under equilibrium, right. So and slight changes from equilibrium, this equation works. So, how do I infinitesimally, so how do I interpret this equation? How do I infinitesimally change the internal energy of the system? I have to infinitesimally change the entropy of the system, and I have to infinitesimally change the volume of the system, right. And correspondingly the temperature, whatever is the temperature, right, so of the system, and whatever is the pressure of that system, that changes, so this equation tells me the pathway of changing the internal energy of the system, right. Or in other words, I can say I can change the internal energy of the system, right, if I have control on the entropy and if I have control on the volume, right. So, these are the independent variables that if I have a knob on them, I change the volume of the system, slightly I increase the volume or slightly I decrease the volume, I can change the internal energy of the system. Slightly I decrease the entropy or slightly I increase the entropy of the system, I can change the internal energy of the system. Since I am doing these infinitesimal processes, these are all quasi-static processes, right. So, this equation, you may ask why you derived it from a quasi-static equation, but so you are saying that this is a general equation. It is a general equation because all these processes, the way you interpret them is changes are infinitesimal. So, they are quasi-static by definition, okay. And u itself as a variable then so the way to change u is either I change S or I change V, right. So I change u just by slightly tuning S or slightly tuning V. Okay. So that's the way to interpret this. Okay. So this is this is I am going to write this as equation number 2. Okay. All right. So let us keep this in mind from now on, right. So we are going to write a lot of differential quantities, and in these differential quantities everything is quasi-static, and the first thing I am going to look at is or the first potential that I have is the potential called internal energy, and internal energy changes as a function of state variables as TdS minus PdV. Okay. All right. Now actually I said using statistical mechanics temperature is not a very fundamental quantity, right. Turns out that in StatMech, which in some sense is the BAP of thermodynamics, right. So if you see my other course, I do a bit of StatMech, right. So this material design course, this is also an NPTEL. So there I do a bit of StatMech and say how StatMech relates to thermodynamics for closed systems essentially. So StatMech which is a BAP of thermodynamics, so the way StatMech is developed is S, U, these are all more fundamental than temperature, pressure, right. So these are all derived quantities. Right. So entropy, internal energy, these are all something that I can calculate, right, by looking at the number of states. I have a definition for entropy, I have a definition for internal energy. I look at my solid, if I am looking at solids, right, as spring mass systems which has both potential energy and kinetic energy, and I can calculate my internal energy, right. So these are all definable. Even for non-equilibrium systems I can define what entropy is, what U is, but I cannot define what temperatures are, right. So essentially so StatMech defines temperature using this equation essentially, right. So as dou S by dou U, once I keep the volume as constant, I am not changing the volume of the system, I am looking at if I change the internal energy, how much does the entropy change, right, and based on that I am going to define what the temperature of the system is. Okay. So and in fact you can go on and then understand temperature from a StatMech perspective using this definition of temperature. Okay. Similarly I can define pressure, right, from this equation where so I am just going to define pressure as dou S by dou V, but that is to be taken at a constant entropy, constant internal energy, right. So dou S by dou V at a constant internal energy, I am not changing the energy of the system, whereas I change the volume of the system and I see how much the entropy of the system is changing. Entropy is that fundamental in StatMech, right. So this tells me the definition of pressure, of course along with this equation. Okay. But let us not bother too much. I mean that's something because so it's always good to relate between fields. So I keep giving you this what seem like new distractions, but so this is something you can keep in mind, but it's not very relevant now. Now we are going to take temperature and pressure as something which is very fundamental entities. Okay. All right. So this is so this is the equation, and then U is the first thermodynamic potential, right. So let us keep it that way. Okay. Now let us go to closed systems like I promised, right. What happens in a closed system? In a closed system, ds plus ds surroundings is always greater than or equal to 0, right. Now in a closed system, now I am going to define new thermodynamic potentials, right. So just to give you what is coming up, I am going to define new thermodynamic potentials that depend only on the system, right, or some parameters of the surrounding that can be dumped into some temperature, pressure sort of thing, right. And so I do not want this equation. This is the second law of thermodynamics. but this is telling me that the entropy of the universe is greater than or equal to 0. This is not very useful for me, right. So, I want to actually understand more useful things about the system in of interest to me. Okay. All right. Now, ds I can have whatever non-equilibrium process, equilibrium process. So, let us not worry too much about the ds, but I have a surrounding. Whatever may happen to the system, the surrounding is always in equilibrium, or surrounding is a reservoir that so I can dump in a lot of heat into the surrounding, but it is going to change its temperature very nicely, right. I can dump in whatever work I want into the surrounding, but it is going to change its pressure very nicely, or volume so it is going to expand or contract in a very quasi static manner. So, surrounding is always in equilibrium or always quasi statically changing, right, and in some sense surrounding is also called a reservoir, right. So, I can just so surrounding is a reservoir of temperature. So, surrounding has one particular temperature T prime, right, surrounding has one particular pressure P prime, and this surrounding imposes its if the system is in equilibrium with surrounding, right. So, this is system, this is surrounding. Until here the temperature is always T prime, the surrounding is always in equilibrium with itself. But if system is in equilibrium with surrounding, then the system's temperature should be T prime, right. But it is not necessary that system is in equilibrium with surrounding. System can have some explosive chemical reaction happening where I do not even need to define the temperature of the system, right. But the surrounding or the interface of the system with surrounding has a temperature of T prime. The interface of the surrounding with system has a pressure P prime, right. So you can imagine the system to be your a substrate with a film that is going to grow on it, right. The surrounding is everything else, right. So, I can actually control the temperature of the surrounding, I can control the pressure of the surrounding, right. So, these are some things that are in my control. I'll come back to this, right. So, I'll come back to this when I give you example of a vacuum chamber. Okay. So T, I am going to define this as T of surrounding, but this is also the same as T of interface between system and surrounding. P is the P of interface between the system and the surrounding, right. So, I am just going to write it as T however you might want to T bar and P bar. Okay. Okay. Now, let us then write this equation of ds plus ds bar is greater than or equal to 0, where ds bar now, what is ds bar? Ds bar is it comes from the first law of thermodynamics, that is dE plus P dV, but then E, everything is for the surrounding, dE bar plus P dV bar, right. So, what I have, if I look at this equation, right. So, this is equation 3, let us say. Equation 3 then turns out to be ds plus dE bar, which is that of a surrounding, plus P dV bar is greater than or equal to 0. Okay. Now, if my surrounding energy is E bar, or I change the energy of the surrounding by dE bar, how much I changing the energy of the system by? This is dE, right. So, because dE bar plus dE should be equal to 0. The net change in energy, this is again first law of thermodynamics. Energy is a conserved quantity. I can neither create energy nor destroy energy in the universe. In the system, I can exchange energy with the surrounding, right. Or I think I am writing U, right. So, let me just write U. Okay. So, the energy can be exchanged between system and surrounding, right. So, whatever is the change in the energy, internal energy of the system, of the surrounding should come from the system, right. So, the negative of the system's energy, right. So, that is energy conservation essentially. Similarly, there is also volume conservation. If my surrounding has expanded, that should come at the cost of the system. Now, you may say is the volume of the universe constant or something, but we can assume for our thermodynamics sake that the volume of the universe is a constant, whatever things that I have, right. So, everything is happening in a closed vacuum system, vacuum chamber, right. The total volume of the vacuum chamber plus the system of interest is a constant, right. So, but if there is some change in the volume of the system, that is the system is expanding in volume, then that should come from the surrounding, right. So my system has expanded in volume, so the surrounding has reduced in volume, right. So you can imagine it for day to day life circumstance. That's my universe is just a vacuum chamber, it is not anything beyond the vacuum chamber. Okay. All right. So using these two, I am going to say that ds bar ds plus now so I am going to use this, right. So this is equation 4. Equation 4 transforms as ds plus now du is going to be written as minus du, right. So that is the u of the of the system. I am trying to write everything in terms of system, right. So that is my eventual aim, right. So this is converting surroundings to system. These two are to convert surrounding parameters. I do not want to know the surrounding energy, right. I do not want to know the surrounding everything that is happening in the how the surrounding is changing its volume. I do not want to know that. I am just saying that okay, if system changes its volume, surrounding has equivalently changed its volume. What is happening in the surrounding, I do not care. How is system changing its volume? System is changing its volume by accepting more gas molecules and increasing the volume of my thin film that is growing, right. So convert surrounding to what did I say, system parameters. Okay. So ds minus du, s is again of the system, u is of the system, I am happy so far, plus there should be there is a divided by t, right. So du plus p dv divided by t bar, right. So t ds actually goes here, right. This is 1 by t bar or t ds equal to this. Okay. So t ds minus du plus p of surrounding dv, but I mean that plus also becomes a minus because now I am going to use the volume of the system, not volume of the surrounding, is greater than or equal to 0. All right. Okay. So something came up here, right. So t ds minus du minus p dv is greater than or equal to 0. Let us box this and say that this is my equation number 5. All right. Most of it is in terms of the system variables, right. So S is that of the system change. So I am changing the entropy of the system, I am changing the entropy of the internal energy of the system, right. I am let me write it in a different color. I am changing the entropy of the system, I am changing the internal energy of the system, I am changing the volume of the system. So that is good. Just the temperature and pressure are that of the surrounding, but the surrounding pressure and temperature, surrounding is always in equilibrium and these are nothing but the interface temperatures and pressures, right. P is that of the P interface. Okay. Now with that caveat, I am also going to throw away T tilde and P tilde and I am just going to call it T and P with an assumption that T and P are where the interface of the system with the surrounding, that has a definable temperature and definable pressure. The system itself, if it is exploding, does not need to have. If I have a Deepavali cracker which is exploding and that is my system and I want to see if it is exploding, I am not going to define temperature of that system, right. I am saying this Deepavali cracker is in a surrounding of atmosphere that has a certain temperature, and that temperature is defined by the interface between the system and the surrounding, however you define the system and the surrounding. Okay. So now that is a reservoir, that surrounding is a reservoir that has temperature as defined by the environmental department that day, right, or you can actually look at the temperature of wherever you are celebrating your Deepavali. Okay. So essentially this is so T and P, I am going to just write now this equation as T ds minus du minus P dv is greater than or equal to 0 with a caveat that T and P are the definable temperatures and pressures of the interfaces between the system and the surrounding. We'll develop it even more. Okay. All right. So now let me then say that I have a system, okay, of a constant volume. Okay, this is case 1, closed system, right. So, which means the system can exchange its energy with the surrounding, but this closed system has a constant volume. Then this equation, which is the same as equation 5, transforms to minus du Tds is greater than or equal to 0, or du minus Tds is less than or equal to 0. Okay? Okay. If that is the case, because dV is 0, right. So, dV is equal to 0. So, I have an equation now du minus Tds is less than or equal to 0. Based on this, I am going to define a functional called f, right. So, this also has units of energy. So, this is some kind of an energy, right, which is equal to u minus Ts, right, and this I am going to call it a free energy, right. I will tell you why this is a free energy. It is not completely, it is not changing the internal energy of the system, you know. So, there is some degree of freedom that I have, that only will change, right. So, that is called the free energy, and this is called Helmholtz free energy. Right, and this equation is actually telling me that dF is less than or equal to 0, right, for the system, right. dF less than 0 means system is proceeding towards equilibrium. dF equal to 0 means the system is at equilibrium. Right. If I have a constant volume system, let us say, right, and then there is an explosive reaction, right. So, for example, okay, so let us take this example of again the 4 gases H2, O2, argon and nitrogen, but this time, you know, so they can exchange, these are not completely sealed. So, there can be exchange of energy. System and surrounding, right. Then I break these barriers, right. If I break these barriers, you know, all this entire system, right. So, if I calculate the F as a function of time, right. So, if I calculate this free Helmholtz free energy as a function of time, this Helmholtz free energy is just going to decrease until these have completely mixed and until I have achieved an equilibrium, right. So, they are mixing, while mixing also I can define this Helmholtz free energy, right. So, when they are completely vigorously mixing here, in fact it is in a non-equilibrium state, right, that is okay. So, but then my dF has this pathway where it is actually decreasing, right, it is decreasing towards you know, some sort of a saturation where dF equal to 0. What is the advantage of this? Here I just care about my hydrogen, oxygen, argon, nitrogen, and I don't care about how much energy it is exchanging with the surrounding. How is the surrounding changing? I don't care about it, right. If it is an isolated system, well and good, I can just look at the entropy and I can see how entropy is increasing with time, right. But here it is not an isolated system, here it is an closed system or an open system. So, the potential of interest for me is a Helmholtz free energy because it is a constant volume system, right. Where does this process end, right. You know, so that is determined by, you know, so this process goes in the direction of equilibrium and that is determined by when is dF equal to 0. Okay. Now, there are a lot of things that you know, so constant volume right, is a constraint that happens mostly on computers, right. So, people doing simulations, right. I have molecules that are trying to react with other molecules. I make sure that everything is happening, you know, so there is some hydrogen molecule which is going to react with oxygen molecules. So, this is hydrogen, let us say this is going to react with oxygen molecules, let us say water to form water or whatever is the reaction, right. And all this is happening in a closed closed system, of course, which means they can exchange energy, but all this is happening in a constant volume cell, right. If I am doing my Monte Carlo simulations or whatever, I am doing everything in a constant volume cell. So, what I am going to do is I am going to track f as a function of time, right. I set the simulation and then I define Helmholtz free energy, and I track f as a function of time, and this f as a function of time whenever it has reached the minima, that is when I say that okay, now I have come to an equilibrium where hydrogen has reacted with oxygen and formed the hydrogen dioxide or water in that sense. Okay. So, so this is how I look for equilibria. In simulations, I just put every reacting species. I say that everything is happening in this confined volume, that is my system, and I am tracking the Helmholtz free energy, right. When the Helmholtz free energy, initially these are all reactive species, which means they are all under non-equilibrium, but the f, if I track it, f is going to nicely reduce and come to some kind of an equilibrium as a function of time, right. And at that equilibrium, so I have enough water, enough hydrogen, enough oxygen, everything coexists with each other in a very nice equilibrium fashion. Okay. Okay, that is the way to understand it in a system, right. So this is when I change the internal constraints, then the pathway to equilibrium is always given as dF is less than or equal to 0. Just like for an isolated system, the pathway to equilibrium is always given as ds is greater than or equal to 0. Okay, so that is the second law of thermodynamics. This is a derivative of second law of thermodynamics, just looking at the system, right. So not the surroundings. Okay, that is if I relax the internal constraints. Now, typically what do? I have so I am, let us say, growing some thin film, right. I want to do this reaction BaCO3 plus TiO2 gives rise to BaTiO3. Okay, I want to do this reaction, right. At room temperature and atmospheric pressure, I put BaCO3 and I put TiO2. They both are in equilibrium with each other, they both coexist with each other, but nothing, this reaction is not happening, right. So no reaction. Okay. But for the reaction to happen, right, I have to say that I have to go to some temperature and pressure, let us say, or volume in this case. I am doing this in a simulation, in a Monte Carlo simulation. I have to go to some temperature and volume where this starts reacting, right. So essentially I am changing the external constraints, right. So the temperature, volume, these are external constraints are being changed. Okay. Now what are these external constraints going to do? These external constraints are going to take the system away from the current equilibrium. Current equilibrium is at T1 at room temperature and atmospheric pressure, and it is going to define a new equilibrium. New equilibrium condition is at T operational and P operational or volume operational, right. Now at this temperature and pressure I am going to evaluate what is the new equilibrium, right. So that new equilibrium can have some barium titanate that is formed, it can have still some barium carbonate that is unreacted, and it can still have some titanium oxide that is unreacted, right. So all these three can exist in different proportions, that is okay, but this is a new equilibrium because I have changed the temperature and pressure, right. So by changing the external constraints I am going to a new equilibrium, right. So first I take it away from that new equilibrium, the system is taken away from that new equilibrium and I give it enough time such that it comes to this new equilibrium, right. So I need to solve this problem, this is the problem of interest to me. I change the external constraints, I do not change the internal constraints is okay, right. So, everything done at the same temperature, same volume, and then let explosive reactions happen, chemical spontaneous processes happen, chemical reactions happen, that is okay. There I am changing the internal constraints, right. But for a growth process, if it is not happening at temperature T1 and pressure P1, I am going to increase the temperature or decrease the temperature to get the growth of my interest, right. So, what is the guarantee that this reaction will happen at the temperature of my interest, right, can you tell me at what temperature and pressure is a new equilibrium developed such that I get my barium titanate, right. So, this is the experiment that I typically do, right. So, I change the temperatures, I change the pressures, or in a computer I change the temperatures, I change the volume, and I want these reactions to happen, right. So, as a result, let us try to interpret this slightly differently, right. So, I have F which is equal to E minus Ts, this is how I have defined S as F as, right. Then the way to change F now is U minus Ts is du minus Ts, right. So, that is equal to du minus Tds minus S dt, right. Now, Ts is so if I just take a differential of that, it is Tds plus S dt, okay, and du itself from first law of thermodynamics is Tds minus Pdv minus S dt, plus Tds minus S dt, right. This Tds cancels. So, df now is equal to minus, I am just messing it up a bit, but let us write it this way. Let us write the math and then try to interpret it, minus S dt. Aha. Now I have now I am going to say, alright. So, what happens, right, now it is no longer true that my volume and temperature are constant, right. So, earlier when I am looking at the internal constraints, I said that alright, you calculate what is equilibrium, you have to calculate F, where is it, df less than or equal to 0 determines my equilibrium, but this is if I only change the internal constraints are temperature is not being changed, volume is not being changed, right. So, the external constraints are fixed, only internal constraints, right. So, this molecules can react with each other, those are the internal constraints, right. Then I say that df less than or equal to 0 determines the pathway towards spontaneity or pathway towards a spontaneous reaction and its corresponding equilibrium, right. But now I am asking a much more formal question, which is if I change the external constraints, if I am changing the volume of the cell and temperature of the cell, right, how am I changing the df, right, such that what is the new equilibrium, how am I going to how am I going to define the new equilibrium, right. With respect to the old equilibrium, what is the f of the new equilibrium, right. And then at that equilibrium, then I change the internal constraints or I fix the external constraints, right. So, V and T, I take volume and temperature to a certain extent and let the reaction happen there. The reaction happening is changes of internal constraints, right. Whatever is the F, it wants to come back to the new equilibrium F, right. But I want to first know what is the new equilibrium, correct. And the new equilibrium, how do I know? I know it from this equation, right. So, the way I change F is by changing volume, right. I change volume slightly, that changes F, or I change temperature slightly and that changes F, right. So, these are the two constraints that I can change to change F, and the new F is given from the old F, or the difference between the new F and the old F is given by this equation, okay. So, that is the beauty of it. Here I am actually changing the external constraints, right, and I am defining the new equilibrium, okay. So, when I say df less than or equal to 0, it does not mean that it is so what does it mean? It means that I fix my external constraints, the pressure and volume, the volume and temperature of the cell are fixed and let the reaction happen, and this reaction will proceed to a scenario where F saturates, saturates, right. So, df is equal to 0, that is my equilibrium, that defines my equilibrium at a given condition. But if I am changing the conditions themselves, if I am changing these external conditions themselves, if I am changing the volume of the cell and temperature of the cell, then I am defining a new equilibrium. right. So, first define that new equilibrium and then see if the reaction is happening at that new equilibrium, right. So, this equation defines for me how F changes, where so how F changes, it tells me a recipe of changing F, right. And how do I change F? I change F by changing the V and by changing the T, okay, the temperature of the interface and the volume of the cell, right, volume of the system, okay. So this is so this is an important, this is the a very important equation that also defines so how F changes, or a differential form of Helmholtz free energy, right. So, this is a differential right. Now, let us assume that so let me just to explain, right. So, again the absolute values of these energies do not make any sense, but just to give you a feel for it, let us say that the F, right, at room temperature and pressure and atmospheric pressure is some value F1, right. So, F1 in energy electron volts or some energy units, right. So, is some value F1 define do not worry, I mean, so I cannot so defining absolute values of energy does not make sense, but so in the same scale, in the same reference, let us say F at room temperature and pressure is at some value F1, right. So, this is the equilibrium F, okay. Now, this equation tells me what is the equilibrium F, right, at okay, at temperature which is slightly higher temperature, and pressure also which is lower pressure, right. So, this is, or sorry, volume, I have to do this at volume, right. So, at some volume V1, this is V2, I have an F2, okay. Now, when I if you see, so I am taking this, I am taking my Helmholtz free energy. So, from by changing the constraints from temperature so if at this temperature, right. So, I instantly go to this temperature, let us say. So, I instantly go to temperature high and volume V2, right, and I am asking the question okay. So, I am just a bit, okay, it does not matter, let us. Okay, so let us say it a bit differently, okay. So, I have F1, right. So, which is the total free energy of this system that I have, which is barium carbonate plus titanium oxide. All this is at room temperature and some volume V1, okay, some system volume V1, right. Now, if this were to react and form barium titanate, right, I have to evolve my F, so the F should decrease, right. So, this should form barium titanate. So, the F for all these three components that exist at room temperature and volume and a given volume should ideally be less than F1 for this reaction to be spontaneous, but I am saying this reaction is not spontaneous. So, the F2 is actually greater than F1. So, this is not a spontaneous reaction. So, then what I am saying is this is the equilibrium F, right, but so just by reducing F I am not going to do this reaction, I have to increase F, increase the value of F, let us say, right. So, what I do instead is I change the conditions, right. So, I take it to F3, which is a temperature, higher temperature and a different volume, right. Now, F3 is less than F2. No, if F2 is greater than, then it will go, but F2 should be less than F1, right. So, then it will not go, right. Now, F3 is less than F2. Now, once I take the temperature to T high V2, right, the F of this reaction is still F2, right. So, at time t equal to 0, the F is still F2. So, F2 will start degrading towards F3 as a function of time. So, I start at F2, right. At this temperature it is going to go to F3. F3 is my equilibrium condition, right. In some sense this is how I interpret it, right. This is at temperature T high and so volume V1 or V2, right. Whereas at temperature T low and volume V1, ideally my F equilibrium is somewhere here, but my F2 is here, right. So, I cannot go in a direction where I increase my F, right. So, that is what thermodynamics tells me. I can only go in a direction where I decrease my F, and that is my equilibrium. So, this reaction is not a feasible reaction at this temperature, but this reaction is a feasible reaction at this temperature. So, I have to actually now go from redefine my equilibrium from F1 to F3, right, and this happens by changing the external constraints. Okay, I hope this is clear now, right. So, I have to change my equilibrium condition from F1 to F3, and that change is depicted from this equation or by changing the external conditions by saying dF equal to minus PdV minus S dt. Okay. So, the way to change dF or the way to change F is by changing the volume of the cell or the new equilibrium F, this is right, is to change the volume of the cell or the temperature of your process. Okay. Okay. So, this is an important potential, this is called the Helmholtz free energy. But I keep saying that Helmholtz free energy is something that is used for used by theorists, right. So, when I have constant volume processes, I do Helmholtz free energy. Turns out experimentally it is always difficult to constrain the volume of your system, right, especially these are open systems, right. So, more mass comes and falls on my thin film growth, the volume is growing, right. So, experimentally it is difficult to constrain the volume of the system. But then what is easy to control? My control parameters can be volume and temperature, but they can be temperature and pressure. Pressure is easier to control. How? This entire field of what is called vacuum technology, where I can make vacuum chambers, right. So, these are actually sealed nice vacuum chambers in metals, right. So, made of metals or glass, right. So, these are vacuum chambers, and vacuum chambers means I should be able to remove gas out of it and put in gas into it, right. So, I will be able to maintain pressure by removing gases, right. So, from the, let us say this is at 1 atmospheric pressure, and I can I can remove gases using what are called vacuum pumps, right. Various kinds of vacuum pumps exist, what are called roughing pumps. I will not go into details of this, you can check it out on the internet, right. So, roughing pumps can take your vacuum from something like, okay, take your pressures from something like 1 atmosphere, which is the atmospheric pressure, all the way up to 10 power minus 2, 1 atmosphere in terms of bars. Okay. So, 10 power minus 2 millibars. Okay. Then you have what are called turbomolecular pumps that can take the pressure from 10 power minus 2, 10 power minus 3 millibar to all the way up to 10 power minus 6, 10 power minus 7 millibar, right. Then you have what are called ion pumps, or something like titanium sublimators, that can take your pressure down from 10 power minus 7 all the way up to 10 power minus 10, or what is called the UHV range, ultra high vacuum range, millibar, and so on, right. So there are some things that I have missed here, cryo pumps and so on, right. So this is something that you can, this is going to be part of what are called vacuum technology courses, right. So that is that I am not going to do here. I want you to take the essence, I mean everything has its own nice technology, right. So how am I removing air molecules from my vacuum chambers, right. So everything has its own nice mechanisms behind it. Please read it, that is a self study assignment. Read about creating vacuum or lowering pressure. Okay. So once you lower the pressure, you should also be able to maintain it, right. So that requires a control system, right. Actually read it and maintain it, right. So you need pressure gauges, pressure sensors and gauges. To maintain the pressure in the vacuum chamber. Once you remove gas molecules, you should be able to maintain pressure, right. So you should be able to know how many gas molecules have you removed and how much pressure have you created, right. So how much vacuum have you created, right. So that happens through pressure gauges, but then these are all control systems. The sensor reads the pressure, and then what is called a PID control exists there, right. So using this PID controls, you can actually set some point at which the pressure should be, and the PID controller, so once it increases beyond that, it will give a feedback so that the pressure decreases. If it decreases below, it gives a feedback so that the pressure increases, so that it stabilizes at some point, right. So PID is proportional integration and then differentiation, right. So it uses all these processes to stabilize your pressure to a set point. So that's again the theory of control systems. Okay. Now the point here is, because of vacuum technology and control systems, we know how to control pressures in our vacuum chambers. We know how to control temperatures, right. So these are thermocouples through which you read the temperature, right, and I know how to heat my materials. This can be resistive heating, this can be IR heating, whatever it is, right. So I know how to heat my materials, and I know how to detect the temperature and set the temperature to that point, right. So this is the advent of control systems and vacuum technology essentially, right. So temperature and pressure are good control variables, right. I will come back and then give you some let us discuss some numbers on how many gas molecules I will be removing at each of these pressures, right. So I know that so that is an exercise worth doing, so that you have an estimate, an idea of what this is, right. But let us just first finish the potential that we are trying to do. Temperature and pressure are good control variables, right. Now so let's now do the internal constraint problem, right. So where temperature and pressure are fixed, and I am seeing when the reactions become spontaneous, right. So fix the external constraints which are temperature and pressure. This is case 2. Case 1 may we fixed temperature and volume, and in case 2 we are fixing temperature and pressure, and vary the internal constraints to understand direction of equilibrium. Okay. Now, so then let us go back to this equation. Before defining F, we have said, yes, here. So TdS minus du minus PdV is greater than or equal to 0. TdS minus du, sorry. but now I fix temperature and pressure. So, this equation then becomes right. So, P is a constant. So, this then becomes d u minus T s minus plus P v, right, that is less than or equal to 0, right. So, from here, so just like I have defined u minus T s to be a Helmholtz free energy, now under constant pressure and temperature I can define this to be my potential for the system. Now, I have come back to the system parameters u minus T s plus P v, and I am going to define this as Gibbs free energy. Okay. Why is it called free energy? We will again discuss that, but so essentially dg is less than or equal to 0 for fixed Tp. This defines my equilibrium, direction of equilibrium, right. Now, what about if I change the T and P, right. So, changing the external constraints, the same exercise we did earlier, right. That is going to say d g is u is TdS, sorry, dg is less than 0, right, that is du minus Ts plus Pv, right, that is equal to du is what, TdS minus Pdv minus TdS minus SdT plus Pdv plus Vdp, that is less than or equal to 0, and that gives you dg is equal to SdT or minus SdT plus Vdp. Okay. So, essentially I can define one equilibrium to another equilibrium by changing temperature and pressure, but the way G changes is it is going to change with temperature as minus SdT, and it is going to change with pressure as minus Vdp, right, or in other words dou G by dou T by fixing the pressure is minus S, right. So, the slope of G versus T once I change the temperature once I fix the pressure is minus S, right. So, I can fix the pressure, change the temperature, right, and calculate how G changes, right, or I can fix the temperature and change the pressure and see how G changes. So, G changes both by changing temperature and pressure, and both temperature and pressure are good control variables. In a process I can control both temperatures and pressures, right, and then the available energy to the system that is changing by immediately changing by changing temperature and the pressure is the Gibbs free energy, right. That is the free energy that I change. I am changing internal energy in some complicated fashion, I am changing some other so entropy in some complicated fashion by changing temperature and pressure, but the immediate thing that I am changing, and I have a recipe to calculate it, is the free energy that I am changing, right. So, that is freely available energy for me that I know how to change just by changing pressure and temperature, that is Gibbs free energy. Okay. So, by changing the external constraints temperature and pressure I am changing G, and this gives me how I am changing G from one equilibrium state which is at one temperature and pressure to another equilibrium state which is another temperature and pressure, right. And then the same discussion that we did for Helmholtz free energy also operates for the Gibbs free energy. Okay. Okay. So, with that let us actually stop here, right. So, and then we will develop from the definition of what Gibbs free energy is, because this is more relevant to all the experiments, all the materials growth experiments that we do. So, you actually see that all the materials growth people speak about delta G's, right. It is always about delta G's. Okay. Whereas if you talk to theorists they always talk about Helmholtz free energies, right. So, it is because so what are you constraining essentially, right, and once you constrain so what are these variables that I can change that immediately reflect in a free energy, and that immediate reflection in free energy is temperature volume which is Helmholtz free energy, temperature pressure, that is Gibbs free energy. Okay. Okay, so both of them derive from second law of thermodynamics, both of them speak about the system particularly, not the surroundings. All the details in surroundings are not of interest to me, right, and both of them are very much applicable to closed systems. It depends on what sort of constraints you have in your closed system. Okay. All right, so with that let us end here and let us again meet in the next class. Thank you very much.